Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff, the great stuff. And I am super happy to have Henrique Reggiani with us today. Hey, Henrique.
Hello, Frank. Hello, Frank. Really nice meeting you. Really good to be here. And thank you for the opportunity.
Well, it's a very awesome article. So I'm always happy to go through awesome articles. So thank you very much. Let's see. Henrique, where are you at?
So right now, I'm working at the Carnegie Observatories here in Pasadena, sunny California, having a little sun every day, nice weather. And I'm
Well,
recently, and I am recently a research fellow here.
very cool. Very cool. So it's now Dr. Reggiani.
Yes.
Did you go to the AAS 240 meeting in Pasadena this past year?
I didn't have the chance to go because I, at the time, was visiting family in Brazil, and I got here by the end of that meeting. But I saw some people here. I met with a couple of collaborators, so I
Good.
got here just at the end of the meeting,
Good.
as
Well,
a matter of
maybe I'll
fact.
see you in Seattle for 241 or whatever it is. So,
Yes.
so you can usually find me on the exhibit floor in the AAS publishing booth. So that's a good place to find me.
Okay. I will find you there.
Yeah, please do. So it is July 29th, 2022 as we shoot this. And I'm in Phoenix, Arizona, and it's definitely sunny here. Although we did get rain this morning. We got quite a bit of rain this morning. So this is the rainy season in Phoenix. So yeah.
Oh, no rain here for a long time.
For a while, yeah. California's got a little drought
Yeah.
thing going. So yeah.
Yeah.
Okay. Enrique, what do you like to do for research?
Well, so mostly what I do is that I try to use metal poor stars to understand a little bit of the evolution of our galaxy, mostly galactic archaeology, a little bit of nucleosynthesis, and mostly the formation of the galaxy using these different chemical aspects of metal poor stars.
Very cool.
I think that sums it up pretty well.
That's a very awesome topic. And this is going to bring us to this very lovely AJ article. Open access, people. You can go get a copy for free. Go get it. The chemical composition of extreme velocity stars. And Henrique, take us away.
Okay, so this paper actually has a very interesting history because a couple of years ago, I was studying a pair of binary stars, and they had this very different chemical composition. And after Gaia DR1 came out, we found out that these binary stars were traveling at very high velocities. So I got interested in trying to look for these extreme velocities, these extremely high velocity stars. But I ended up that I didn't have telescope time to observe them with. But a couple of collaborators, and particularly Alex D, they were actually trying to look for these stars because of something else. They found out that the first stars that they observed with an extreme velocity in their initial sample is a star that is known to be neutron capture enhanced. It has an extremely high R process, and they thought maybe all of them do, and they started a project to observe some of them. And I got in contact with them, and then I said, "Oh, I have this idea. I want to study this type of stars. I need some telescope time." And they said, "Oh, we already have observed these types of stars." And that's kind of how we got involved together, which ended up in this paper.
Very nice. Very nice.
Just a small introduction to how we got here.
Yeah, how we got here, right?
How we got here.
How you ended up as first author, right?
Yes. Okay, so going to the actual paper. So first, a little bit of an introduction what we're talking about when we say these extreme velocities. So there was this idea in the end of the 80s that stars in the bulge of the galaxy could interact with the black hole in the center of the galaxy. And if they did have an encounter with this black hole, and it was a binary pair of stars interacting with the black hole, one of the stars could be expelled from the system at velocities exceeding 1,000 kilometers per second. It could actually go to up to 4,000 kilometers per second. And Hughes, when he proposed the mechanism, he said, okay, if we find these stars, it means we have a supermassive black hole in the center of the galaxy. It would be proof of the existence of this black hole.
Okay.
And it started there. And going from there, there was some theoretical work for quite some time, but the first time anyone actually discovered one of these stars was about 20 years later. They found a star that was unbound from the galactic potential at about 850 kilometers per second back in 2005. And once that paper got published, a lot of interest started rising again on the subject of actually seeing these kinds of stars. And a few ideas were brought back on how stars could be accelerated at extreme velocities, for example, you have a binary system, one of the stars explodes as a supernovae, and the other star is accelerated as a result of the explosion. And other ideas were brought forward, like, for example, these stars can be tidal debris from dwarf galaxies that were recently disrupted by interacting with the Milky Way.
Okay.
So a lot of momentum started happening for these stars, but because of observational difficulties, we didn't have a lot of proper motions. It took us quite a while to be able to actually start finding these stars in a more statistical sense.
Yeah.
And that's basically when Gaia DR1 was released. And then we had proper motions. And for all of the stars for which we already had some sort of radial velocity, we actually started measuring stars.
Very cool.
With extreme velocities. So back in 2018, there was a paper by Herzog Arbeitman. I am sorry if I am butchering the name. And they actually published a list of Gaia DR1 stars with extreme velocities. And apart from that, we had a lot of other discoveries, very interesting discoveries. Like, for example, this discovery by Shen in 2018, in which he reported 3 white dwarfs with velocities exceeding 1,000 kilometers per second. That was seen as the result of actual type 1a interaction. He actually can show that one of these stars can be traced back to where we actually saw a type 1a supernovae, which was quite interesting.
Very cool.
We also found an hypervelocity star that can be traced back to the Large Magellanic Clouds. And recently, we have found a star with a staggering velocity of 1,700 kilometers per second.
Wow.
Just moving away from us and going out of the galaxy at really high speeds.
There we go. There we go. Wow.
Now, the thing is that most of these stars are massive A, O, and B type stars.
Okay.
So they are very, their photosphere is very hot, and it's very, very difficult to study the chemistry of these stars. And as we now know, the chemistry does tell us a lot of information about where a star was formed and how that star was formed, what their progenitor system was. So what we were looking for here is, so let's try and look for these extreme and hypervelocity stars, but in F and G type stars, basically dwarfs or giants also, but stars for which we can actually measure chemical abundances in their photospheres.
Yeah.
And we found 15, we observed 15 candidates from 2 different papers.
Okay.
From Hattori 2018, I just want to call out the papers because I think it's really good papers to read. And Herzog Arbeitman 2018 also. One from Gaia DR1 and one from Gaia DR2 data.
Okay.
Now, one of the things that Gaia DR1 didn't have with as good a precision as now Gaia DR3 is our radial velocities. So obtaining spectra of these stars also allowed us to increase the precision of the estimated total velocities of these stars, because now we have precise radio velocities from optical spectrum. So we observed these stars, we calculated their velocity, and we found out that mostly those stars that have Gaia DR2 radial velocities, the radial velocities that we found completely consistent with Gaia DR2 radial velocities. And I just want to call out for that. So now with Gaia DR3, we have a lot looking for us. And I also want to mention the star HE1523, which is the original star I mentioned my collaborators started looking at, the R-process, extreme R-process star, which is also an extreme velocity stars.
Wow, what a combo.
And yeah. And then I think we can go to table 1 and talk a little bit about our observations. So we looked at these 15 hypervelocity stars, extreme velocity stars candidates at the time, with 2 different instruments, one in the Northern Hemisphere, which is AAS at the Apache Point Observatory, the 3.5-meter telescope there, and Mike at Las Campanas Observatory, one of the Magellan telescopes. So the resolution with which we observed all of the stars is pretty much the same. It's around, most of them were observed with a resolution of about 30,000, but a couple of our Mike observations have resolutions ranging from 50 to even to 80,000. So there's a little bit of a variation there. Yeah. And also because of atmospheric observing conditions, etc., we have a lot of varying spectral quality, varying signal to noise in the blue and in the red regions, which in the end means that for some stars, we will have larger uncertainties. For other stars, we will have smaller uncertainties in our final analysis. But all of them were observed in the most homogeneous way we could, given that there are 2 instruments and different observers doing the observations.
Right.
And then again, this is just a log of the observations, some signal to noise ratios to show the quality of our data.
Yeah, very good.
And the first thing we did was calculate the radial velocities, like I already mentioned. And then we moved forward to trying to get the stellar parameters of these stars. Now, also because there is a variation there in the quality of the spectrum, we didn't want to use only the spectrum that is available to calculate the stellar parameters. Now that we have Gaia parallaxes, we have a lot of photometric data available for us. We tried to use all of this available information to get the best possible stellar parameters for these stars, meaning effective temperature, surface gravity, and metallicity of the stars. So this is a list of all of the sources that we used to fit isochron models to these stars. So it's Gaia parallaxes and distances from based on Gaia parallaxes. We have photometry from SkyMapper, JH and K, Gaia, and Allwise. So we have the full black body curves of all of these stars, which give us really good temperatures. We're using the parallax, we get really good surface gravities, and then it leaves us with metallicities taken from the spectrum, which is the best way possible because you actually measure all of the lines. Now, we did a process of calculating these stellar parameters using the isochrones, making sure that the isochron inferred metallicities are the same as the spectroscopic inferred metallicities, so that everything is self-consistent. And once we had all of the stellar parameters for all of the stars, we decided to go ahead and test one of our stars against really well-known papers that had already worked, other studies that had already worked on these stars. And to do that, we used this R-capture enhanced star, which has been studied many times. So we compared our measurements of this star with 3 different papers.
Okay.
So the original discovery paper back from 2007, it used similar ways of calculating the effective temperature from photometry, but spectroscopic way of calculating surface gravity and microturbulent velocity. Okay, and we found out that our result is consistent with their results also. So yes, you see ours on the top there, and this study is lower. So the second thing that we did was compare our results to a data-driven method, which is the new method of calculating everything, and from Rave spectrum, which is not so high resolution, but statistically very significant because they had a really, really nice, well-studied sample for this analysis with Rave. And what we found out is that our stellar parameters also do agree with these data-driven results. So that gives us a lot of confidence in how we did our analysis. And finally, we compared it to a more recent work that did something very similar to ours, including using the same radiative transfer code for their initial calculations. And then the difference between our study and this is that in the end, they used 3D non-LT corrections for the iron abundances to get the detailed metallicity and the detailed temperature and log G, which we did not in our study. And yet, both of our studies agree within our uncertainties pretty well. Good. So once again, comparing with these three very different studies, we are very confident that any systematics that we have in our study and the use of this particular set of isochrones that we use for our analysis is minimal, and we think the expected uncertainties of different works.
Good. Okay.
I already talked a little bit about this, but afterwards we used our radial velocities from the spectrum and the proper motions from Gaia. And the distances we inferred using our isochrone analysis, which are completely consistent with Gaia parallaxes and Baylor-Jones to 2021 distances also. So we use this data set to calculate stellar orbits using Milky Way potential 2014. And we use that to calculate total energies, maximum distance from galactic plane for these stars, their eccentricity, apocenters, pericenters, all of these orbital parameters. Now, one important thing for me to mention now is that at this time, we did not add the potential from the Magellanic Clouds into our model of the orbital analysis. And that could be important for these stars for reasons we'll discuss in a bit.
Depending where they are. Yep.
In a bit, yes. So after calculating the total velocities, we found out that the total velocities of these stars range from about 250 kilometers per second to 580 kilometers per second approximately. So none of the stars in our sample are unbound for the galactic potential. We are considering here about 600 kilometers per second to be unbound. However, they are on the tail of the distribution of galactic velocities for the halo of the galaxy. Okay, once we had all of that, we started having a look at their chemical abundances. So we tried to measure chemical elements from all nucleosynthetic channels. So we measured the light and alpha elements, we measured iron peak elements, we measured neutron capture elements. Most of our measurements were done using equivalent widths. And these equivalent widths are based on two different line lists, one from G2020, which was designed for more metal poor and giant stars, and from Reggiani and Melendez 2018, which was a line list that we designed for more metal-rich stars, because we do have a range in metallicity in this sample that we are discussing here. So we use this a mixture of these two different line lists to make sure we could account for everything.
Good.
And we calculated all of the chemical abundances of all of these different elements in our 15 stars. And once again, we used HEE 1523 to compare the chemical abundances that we obtained to previous works.
Yeah, gold standard.
I think we can go down a little bit, Frank. We can skip this table for the moment. I think we can talk about it.
All the details.
Yes.
Of...
All of the chemical abundances are there. All of the detailed stellar parameters are there. But again, we did compare the abundances of our main star with 3 other different studies and found out that at the most, we have a difference of about 0.1 DEX that could be caused by unaccounted for systematics, which is actually a very good result.
Reasonable number, yeah.
Yeah.
Cool.
And then we can actually talk about the more interesting stuff, which is, to me, particularly, what's the chemistry of all of these stars look like and what they can tell us. So we have a couple of plots that look like the plots that we are seeing here. Each of these plots are divided into nucleosynthetic channels, or at least how we usually divide them. So the first one looks at the alpha elements and titanium, which is technically not an alpha element, but we usually talk about it like an alpha element because similar abundances. But anyway, in all of these plots, the colors and symbols are going to be the same, and they include stars from bibliographic sources that analyzed stars with high resolution spectroscopy using methods that are similar to ours, not always the same, but similar enough to ours that we can compare our analysis directly to theirs. And we include stars from the outer halo of our galaxy, particularly from the first stars program, and this is Chiral 2004. And Jacobson 2015. So it was a large program with a lot of giants and dwarf stars, and we are only including the giants here.
Oh, okay.
So
that's good enough.
We include stars from the inner halo of our galaxy. Those are the axes or crosses.
Yeah.
We include the classical Nissen and Schuster sample from 2010, which includes stars that were thought to be formed in our galaxy. So the high alpha stars, the low alpha stars are stars that are interpreted as being formed outside of our galaxy and then were later accreted with the dwarf galaxies that were formed at. We include stars from the galactic bulge.
Yes, this triangle.
And those are mostly the more metal-rich stars, and it's kind of difficult to find the blue triangles there.
Here.
And we include stars from dwarf spheroidal galaxies. So we include stars from not all of the dwarf spheroidal galaxies, but the most massive ones. So Carina, Fornax, Sculptor, Sagittarius, and from different data sources.
Cool.
And what we wanted to do is to see how the abundances of these 15 stars compare to these different data sets and position our star, the formation of our stars in possibly different environments. Basically, are these stars formed in the Milky Way, or were these stars formed outside of the Milky Way and then accreted onto our galaxy? This was the initial goal. And if you look at the magnesium plotting in particular, because that's an element that is usually easier to measure, the lines are clear, all of doesn't have a lot of non-AT 3D effects that we know to affect it heavily. So it's a good diagnostic tool. And it also has a good variation between the high alpha stars and the low alpha stars. Now, the first thing that called our attention to this plot is that all of the stars that are at a metallicity of -1 and above they all seem to track pretty well with the sequence of stars that were formed in dwarf galaxies.
Okay.
So they do not trace the Milky Way sequence at all. And you can also see that in the plot of calcium below. So calcium, the difference between low alpha and high alpha is not as clear, but from -1 to -0.19, which is our most metal-rich star, you can see that they are closer to the low alpha abundances than to the high alpha abundances, although not as clear as in the magnesium plot. And you can also see that a couple stars, in particular this one star with the larger uncertainty with magnesium below 0, they also seem to be on the low abundance end, which would be a way of diagnosing that these stars were likely or possibly formed in another galaxy and then accreted onto the Milky Way.
I'm with you.
Now, of course, it's only a couple of abundances, and we have to look at in a little bit more detail at the rest of the abundances. Now, magnesium, calcium, silicon, and titanium are good diagnostics because we understand their formation, the nucleosynthesis well, and we do know that the correlation with iron at least for the Milky Way, is pretty well defined. We do know that for the Milky Way, low abundances below about 0.3, 0.4 only start to occur at metallicity of -1, which is where the knee, what we call the knee of the galaxy is at. So anything below that should have been formed outside of the Milky Way, or could have. Okay, so as a preliminary result, based on the alpha elements, we would say that at least the stars with metallicities of -1.5 and above possibly formed outside of the Milky Way, with a couple of the lower metallicity end also being interpreted in that way, but with large uncertainty, so not as likely. Yes, like that star, for example. Yeah. And then
shows up
here,
shows up here.
And all of the same stars appear kind of in the same locus of low abundances in all the 4 panels. So it's not a fluke of one abundance or another.
Right.
Yes. Yeah. So it gives us a little bit of confidence in the interpretation of the alpha abundances. Now I think we can go to the second figure. So we're gonna look at the light odd Z elements, which is sodium, aluminum, potassium, and scandium. Now, these are a little bit harder to interpret because sodium, aluminum, and potassium, they have very strong non-LT effects for the lines that we are able to measure, which means that we have to proceed with caution when measuring them. We have to do the non-LT corrections as best as we can, which we try to do for all of these chemical elements. But the interpretation is also more complicated because their nucleosynthesis depends on the metallicity of the progenitor star. So it is not as easily interpretable as something that came directly from core collapse, like the magnesium and silicon and the other alpha elements. But we do know where the locus where most of the abundances in our galaxies lie. Like, for example, for sodium, the behavior of our abundances at least for the 2 most metal-rich stars is pretty clearly different than the locus of our own galaxy. It's pretty much dwarfs for all the behavior and this low alpha from Nissen and Schuster 2010 locus, which is also dwarf galaxies.
Okay.
Again, we have a couple of stars that could be either one or the other, larger uncertainties. But again, the same thing appears to happen here, that for -1.5 and above, they are closer to dwarf galaxies, and at lower metallicities, a couple of stars are closer to dwarfs and a couple of stars are closer to the Milky Way. So we have a similar interpretation of the results.
Okay.
Now for aluminum and for potassium, it's a little bit harder to interpret because not a lot of data to compare it to,
True.
at least from the samples we drew from the bibliography. And as you can see for potassium in particular, the other samples were not corrected for non-OT effects, the other two samples that are there, but ours was. So there is a larger difference there that is difficult to interpret.
Right. But you got
and for scandium, we see a lot of dispersion in the data, a lot of scatter in the data. So again,
yes,
it can mean for the -1.5 and above, we see that they're closer to the dwarf galaxies once again, but it could just be a matter of data dispersion. And we are careful to were careful to overanalyze this particular 4 plots as meaningful evidence of where these stars were formed.
Okay.
But sodium in particular does strengthen our arguments based on the alpha elements.
Yes, I'm with you.
Yeah. And then we move to the iron peak elements, which are a little bit more diagnostic.
Iron group.
Now, I'll start by saying that why they are a little bit more diagnostic. So based on a lot of different recent results, studying nickel and manganese in particular, both in the Milky Way and in dwarf galaxies, we are now, we think that most of the thermonuclear explosions or type 1a supernovae that enriched the interstellar medium of the Milky Way came from thermonuclear explosions of near Chandrasekhar mass or Chandrasekhar mass events.
Yes.
And in the dwarf galaxies, on the other hand, it's mostly sub-Chandrasekhar mass events.
Ooh, okay.
And one of the differences of having near Chandrasekhar or sub-Chandrasekhar is the fact that for near Chandrasekhar mass, nickel is going to look mostly like what it looks in the Milky Way, which is basically nickel to iron ratio should be around 0. But if you go to sub-Chandrasekhar mass nucleosynthetic events, then you have subsolar nickel, not extremely subsolar, but then again, subsolar. Right. And as you can see, if you look at the Milky Way stars, they're mostly focused on a very straight line close to 0 in nickel to iron ratio. Right. But the stars that are analyzing, there are almost all of them subsolar, and a couple of them, and again, the -1.5 and above, they're all below solar nickel, and they are all pretty well aligned with the dwarf galaxies.
In mix. Yep.
Yeah.
It was triangles again. Triangles was the low alpha. Okay.
Yes. Those is the low alpha focus locus. And then we can look at the manganese, because manganese is very good if you want to talk about Chandrasekhar, talk about thermonuclear explosions.
Yeah.
Because it's almost only produced in thermonuclear explosions. And then you can really see a big difference there, with most of our stars having manganese abundances that are quite different than the very straight line that increases with increasing metallicity for the stars in the Milky Way.
Slightly.
So we do have quite a big difference when we're looking at the iron peak elements, and in particular nickel and manganese, which does provide evidence of two things. First, that at least half of the stars in our sample are stars that were formed outside of our galaxy. And I say half because I'm including all of the stars above -1.5 of metallicity.
Okay.
So there are 4 stars there,
1, 2, 3, 4.
and
Uh-huh.
a few of the stars below 1.5, but have clear low nickel abundances, and also have low alpha abundances that are compatible with dwarf galaxies, although they had somewhat larger uncertainties.
Sure.
So we initially marked those stars as potentially formed in other galaxies and then accreted into our own.
Okay. Mm-hmm.
And from this figure, chromium is not that diagnostic. As you can see, there's a lot of scatter in our data. We are showing chromium 1 because all of our other data is chromium 1, and chromium 1 can suffer from strong non-LT effects, but we did not add any corrections to chromium 1. So it's
Okay.
for us at least, we should interpret it with some care. Should be careful interpreting chromium 1 abundances in this particular case at least. But we also have zinc abundances. And if we look at the zinc abundances, the same that happens with nickel happens with zinc, which is that our stars are quite different from Milky Way stars. So for Milky Way stars, we see an increase with decreasing metallicity for zinc. This is pretty much well known. It's attributed to high explosion energies of very metal poor core collapse supernovae. And nevertheless, again, the most metal rich stars in our sample are quite low, and a couple of the other metal poor stars are also quite low in their zinc abundance, which enforces our argument that the stars, at least half of them, we argue, were formed in a different galaxy and accreted into the Milky Way.
Okay.
Now we have evidence from all of these different nucleosynthetic channels, and we finally had a look at neutron capture. We have evidence from alpha elements and iron peak elements, very good evidence, and somewhat lower evidence from the light or Z elements. And now we have the neutron capture elements.
Cool.
Now we have clearly one star, which has high both slow neutron capture process elements that are high, which is our most metal poor star, and rapid neutron capture process that is high, which is from the European line. So this is the star that we initially started talking about, which is the air process enhanced star.
There it is.
And it was already thought to have been formed in a different galaxy based on the very different type process pattern that it has when compared to other Milky Way stars.
Okay.
And as you can see, for the neutron capture elements, their difference is not as clear. Particularly for strontium, we have a lot of dispersion at the metal poor end, but it's very well behaved at the metal rich end. But this also happens in dwarf galaxies. You also find different dwarf galaxies. So it's difficult. We can't say exactly, oh, this from this or that dwarf galaxies. But if you look, for example, at yttrium and barium abundances, you will see that there are a couple of stars there that have a very high yttrium, have very high barium. It's the same star in this case. A couple of stars that have a somewhat higher barium abundance than the Milky Way, and also consistent with the abundances that we see in these other dwarf galaxies. And just so for people are interested, most of our stars are not particularly are process enhanced. So apart from the one most metal poor star, HE 1523, most of the stars have a distribution of our process that is similar to the Milky Way. It doesn't draw a lot of attention to these stars.
Okay.
Okay, so just to quickly sum up, we have abundances for alpha elements,
Yep.
which tells us that at least the stars with metallicities higher than -1.5 were likely formed outside of the Milky Way and accreted onto the Milky Way.
Okay.
And a few stars at the lower metallicity end that could also have been accreted, but their uncertainties are a little bit larger, so we can't be entirely sure. We do see in sodium that we see the same behavior. So we have two pieces of the evidence from these two nucleosynthetic channels.
Cool.
And then when we look at the iron peak elements, then we do see considerably different behavior again.
Yes.
Because we do see subsolar nickel, which is mostly produced in sub-Chandrasekhar mass thermonuclear explosions, which dominates dwarf spheroidal galaxies and is not the dominant process in the Milky Way, we think. And so, again, for the -1.5 and above in metallicity, it is clear that these stars are probably at this point, more than possibly, formed outside of the Milky Way. And again, some of the stars below -1.5 also formed in the dwarf galaxies and were accreted into the Milky Way.
I'm with you.
And now we have in our sample, if you want the details, you can go to table 3, and there will be a superscript in the names of the stars showing which one of the stars we are attributing to formation outside of the Milky Way. So you can actually see which one of these stars were formed in the Milky Way and outside of the Milky Way. So if you go to the external ID field, you'll see a little C there, a little bit above. So you see,
there we go.
Yes.
Yeah.
So this little C there indicates these are likely stars that were formed in dwarf galaxies.
Okay.
Based on their chemistry.
That's a lot of data on these. Very cool.
There is a lot of data. We did add to this table all of the information we used to do our isochrone fitting and all the information that we got from our isochrone fitting, from the spectroscopic analysis and from the orbital analysis. So it's quite a lot of information for each one of these 15 stars.
Yeah.
Yes. Awesome. It's very detailed.
Very cool.
And very interesting. Okay, so now we have all of this information. We now think we know which stars were formed outside of the Milky Way and came into our galaxy. But we do have their orbital information too. So let's have a look at figure 5. Okay. So now we are showing a plot with angular momentum and total energy of these stars. Now the ellipses there, the shape, or better yet, the shapes, they indicate, ellipses, they indicate the different substructures that we see in the halo and the disk of our galaxy, based on Naidu, based on Bonazza 2020 and Naidu 2021. Okay. So they were kind enough to provide me with the ellipses.
Oh yeah, sure.
So you have their Sagittarius, you have Gaia Enceladus, you have all of these substructures that we have now learned exist in our galaxy, mostly based on Gaia data, right?
Got it.
And like I said before, magnesium is a good indication of either or not it was formed in our galaxy. So for the sake of our argument, we're saying let's divide our sample in two. All of the stars with magnesium that are lower than 0.2 likely formed in dwarf galaxies, and all of the stars in red are stars with magnesium to iron higher than 0.2, which are likely stars formed in the Milky Way, just based on magnesium, for the sake of the argument. And in the background, as gray dots, you see a lot of galactic halo stars. So the background really shows the difference in total energy of our stars. So most of the background stars have total energy in this scale of about -1, -0.5 tops. And our stars are really distributed at much higher energy as a general rule.
Yeah.
Now, the problem is it's difficult to actually tell what this tells us because our sample is biased towards higher energies because we were only looking for high velocity stars.
Right.
So we were already expecting that. So it doesn't actually tell us more than what we already knew in terms of total energy. So they have total energies that are higher than these substructures. They have total energies that are higher than most of the stars in the galaxy.
Mm-hmm.
But there is one aspect of this plot that is quite interesting, which is the fact that we have at least two different locus of stars, two substructures in the plot. So one substructure with angular momentum of about 0, which is the one on top, which is almost a line, one might say, approximately.
Yeah.
So that one could be possibly explained if those stars were accreted in radio accretion events of a dwarf galaxy, for example.
Yeah. Okay. Yeah.
But the second small substructure there, it is interesting because it sits on a place where we don't know any substructure, but they sit together enough that one could potentially think that they belong or are from a same substructure and a different substructure than what we know today. We can't say that for sure because we don't have enough stars. But it is interesting that from our small sample, we did find a small substructure in angular momentum space. And I want to call the attention to that interesting fact.
Yes.
And this is how we are able at this moment, at this paper, to interpret the results of this particular plot. So as expected, high total energies, unexpectedly, two different small substructures in angular momentum space.
Yep.
And as you can see, you have red and blue stars in both places. So you have stars that could have been formed in the Milky Way in both places and stars that could have been formed in dwarf galaxies in both places, which also tells us that, of course, there should be a velocity tail distribution of there are extreme velocity stars that are born in the Milky Way and that were accelerated with different mechanisms, like exemplified by the paper that we mentioned, the Shen et al. Paper that found the 3 really, really fast white dwarfs. And then we can go to figure 6, which is another figure showing the orbital properties of these stars. So this is a little bit, there's a bit more information there. Okay, so in yellow, we have stars from the halo of our galaxy, we know to be halo stars. And in gray, stars from Enceladus, which is this large event of accretion early in our galaxy formation. And we have, the Nix stream that was quite a recent discovery, also added to the plot. Now, interestingly, if you look at our hypervelocity star candidates, or these extreme velocity stars we've been analyzing, you see that there are these 4 stars that are very much higher in total distance from the galactic plane and high eccentricity stars. And all of these stars are blue stars, which are stars with magnesium to iron below 0.2. So stars that we think were formed in dwarf galaxies. So it does provide even one more piece of the evidence saying these stars are not from our galaxy. They were formed and later accreted onto the Milky Way.
Cool. Very cool.
Okay. So now we have all of this information, and what can we actually say about how these stars got to be traveling at such staggering velocities and trying to even leave the galaxy at some point? So we know the stars were formed outside of the Milky Way and accreted onto the Milky Way. So just by knowing that, we can exclude a couple of options. Like, for example, we can say that at least most of these stars were not accelerated during supernovae explosions. There were not binary systems in which binary supernovae happened and they were accelerated because they were not here to initially start. We can also say that they're not from globular clusters because we also do not see any chemical anti-correlations that we usually see in globular clusters. Yes, which we tested, which is not shown in the paper, but we did test that. So that leaves us mostly with three different options, which would be the Hughes mechanism.
Yes.
But the stars are not as fast as the Hughes mechanism proposal. It doesn't have, they're not unbounded. They don't have velocities of 1,000 kilometers per second. So they probably didn't interact with the central black hole. Also, they don't have pericenters that are small enough to say that they interacted with Sagittarius A.
Oh, yeah.
So they're
good point. Yeah.
And they also don't have a chemistry that is compatible with the bulge of our galaxy, because if they were formed in that region, we should have had chemistry that looks like the bulge of our galaxy, and they don't. So we can also exclude that for how these extreme velocity stars were accelerated. And that pretty much leaves us two main options. So the first one is that the stars are large Magellanic Cloud stars. So there are works that show that most of the hypervelocity stars and the extreme velocity stars that are in the halo of our galaxy should have come from the LMC. However, as of right now, or as of when this paper was published at least, only one star had been shown to actually have come to be coming from the Large Magellanic Cloud, one hypervelocity star. Yes, a paper from Evans. And now comes the little caveats that I said at the beginning of our conversation here, which was the fact that we didn't include the Magellanic potential in our orbital calculation. So that could potentially provide additional information as to the origin of these stars. But that being said, their chemistry is not similar to the chemistry of the Large Magellanic Clouds. Yes. And in particular, the chemistry of the lowest metallicity stars, because we don't have a lot of sample for the low metallicity end of the Large Magellanic Clouds. It's really hard to find those stars in there. And so it's difficult to compare because we mostly don't have a lot to compare with. Also, that said, in an earlier paper in 2021, myself and some collaborators showed that all of the stars in the Large Magellanic and Small Magellanic Clouds that we found between minus 2.8 and minus 1.7 metallicity are process enhanced. They have really high rapid neutron capture abundances, which is not the case for these stars. So we do have a couple of evidences that point to them not being from the Magellanic Clouds. Although, again, I say, yes, it would be interesting to see orbital information of these stars with LMC potential included. And that leaves us with the final option, which we think is the best option to explain the velocity of these stars, which is the mechanism that was proposed back in 2009 by Abadi and collaborators. So what they say is that, in a simplified way, of course, is that these stars, they are going to show up because they're the tidal tails of dwarf galaxies that were accreted onto the Milky Way. So the dwarf galaxies are accreted, they interact with the center of the Milky Way, and sometimes a tidal tail forms, and you have stars traveling extreme velocities. Now, they make a few predictions. Like, for example, they predict that velocities should be up to about 400 kilometers per second,
Okay.
which is closer to the mean velocity of our stars. Our stars have a mean velocity of about 360, 380 kilometers per second.
Uh-huh.
So it's right there in the predictions that they made.
Nice.
They also predict that once we start finding a lot of these stars, we are going to actually see substructures. We're going to actually see streams of extreme velocity stars because they are a tidal tail.
Okay.
Of course, it depends how long ago this accretion event happened, and etc. But from the chemical analysis perspective, for example, it is very compatible with this idea because we are not necessarily drawing our sample from a single tidal disruption event, from a single dwarf galaxy disruption event, a single
Right.
tidal tail.
Uh-huh.
We don't know. We are just measuring stars with extreme velocities, and each of
Right.
these stars could have come from different events. And because of that, we don't see their abundances being so tightly correlated, but we see them, they all have, for example, the -1 and above, they all have low magnesium and calcium abundances, but not exactly the same. So it goes to show that different events could have slightly different chemistry for each of their stars, but the result of accelerating stars would be the same. And we would see this evidence on this total energy versus angular momentum plot and this
Right.
eccentricity versus
Uh-huh.
Zmax plot that we were
Uh-huh.
talking about.
Uh-huh.
So
Yep.
it does go to show that the proposed acceleration mechanism from a body is what we think is responsible for accelerating at least 50% or more, actually more than 50% of the sample we are studying in this particular paper.
Of that
And
subset.
of,
Yeah.
and of course, some of these stars we also think are from the Milky Way, and some of these stars could have been accelerated in different scenarios.
Different reasons.
For different reasons. Yes. Yeah. So I think that concludes. We conclude saying that the stars, at least a portion of these stars, were formed in dwarf galaxies. They were accreted onto the Milky Way, and when the dwarf galaxies interacted with the center of our galaxy and disk of our galaxy, they were accelerated to extreme velocities.
Okay.
And we are hoping that we are going to find a lot more of this in the near future, especially now with Gaia DR3 and all the radial velocities that are now available that weren't before.
Cool. Very
Yeah,
nice. Very
yeah,
nice.
yeah. And we do say that in the paper in our conclusions.
Uh-huh.
And I think that yeah, I think that sums up the paper. And just like to shout out for my co-authors and say thank you for all the help in writing it up, and all of the collaborators who commented on my work and made comments when I showed them my plots and the conclusions that I was drawing.
Nice.
Yeah.
Very cool. Henrique, thank you so much for walking us through this very awesome AJ article. Let's see. And you mentioned it a couple times in a couple of different ways.
Yeah.
And so let me ask, where do you think we go, let's say, over the next 2 to 5 years? Are there possibly programs to increase to go from 15 stars to 150 stars or more? And you intoned it a little bit there that there are additional orbit calculations going on where you include some of the perturbing external galaxies, LMC, for example, and others. Are there possibly other wavelength ranges that might be interesting for the abundances? So just kind of, where do we go? What are our next steps in these, trying to figure out these extreme velocity stars?
There are a couple of next steps. A couple of them are being taken. I know of collaborators that are already increasing the sample that we currently have and doing the same type of analysis for larger sample. And I hope that soon we will hear from them and actually hopefully get some more cool information about where more of these stars came from.
Cool.
It is a field that is on the spot, especially with Gaia DR3 last week. or the week before, I don't quite remember which week, we just had a new paper talking about new hypervelocity stars that were found. One of them was extremely high velocity, 1500, if I remember correctly.
Okay. Okay.
So it's a field that is developing with Gaia DR3 precision radial velocities. We have upcoming. We had Apogee DR17 released the end of last year, so we now have a lot of new stars to look for, and cross-matching them with Gaia might provide us new samples of stars to study. And in particular, it might help us because Apogee also looked at the LMC. We might find stars that are coming from the LMC, go into the LMC. And like you mentioned, adding all of these perturbers, as the more perturbers we're able to add in our orbital calculations, as hard as that is, of course, the more information we are going to have as to where the stars came from and where they were actually formed. And that will help us build up even more, in even more detail, the knowledge that we have of the accretion events that formed the galaxy that we live in, and in particular the region we live in, because so many of the stars are close to us. We are finding stars 1700 kilometers per second, only 9 kiloparsecs away from us, which is right here. So I think there's a lot of things going on for hypervelocity and extreme velocity stars, and we're going to see a lot of things in the future.
Cool. I look forward to seeing some of those papers, and we start unraveling some of the origins and mysteries around these extreme and hyper velocity stars. So very cool. I look forward to seeing this. Very nice.
Yes.
And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye-bye. Thank you.
Thank you.